Hi, my name is Bill. I'm from Azendian. So this morning, CK, my colleague, and I, we will share with you how our HVAC energy optimization solution work. Because we have only 10 minutes, so we go quite fast. If you have any questions, we'll be out there after the event. We can discuss in more detail. Basically, our solution today for the HVAC area, I will not talk about our other product. I'll focus only on commercial building. So commercial building, I'm referring to a hospital, office tower, shopping mall, and the lights, right? And the technique we use, is not rule-based. We use AI, machine learning techniques. Just to summarize, the advantage of using machine learning, AI, or data-driven approach is that it's more accurate. False positive is much lower. In fact, the model, which I'm going to be talking about later, the error margin is only 2.5% or lower. So it's actually a highly accurate model. A rule-based model or approach, you're going to get a much higher false positive and inaccuracy, right? So our solution basically achieved three objectives. Number one, improve energy efficient use. I never say reduce use, because if your heat load increase, your energy use will increase. But at every heat load level, how do we use as little energy as possible? And it also enhance, workforce productivity in Singapore. That's very relevant. And lastly, extend equipment life. Right. So I won't touch on the other solution area, just in the center part here. Our solution covers, the chiller, the water side, the AHU, and now we have extended it also, to the space area also. All right. And I'm just going to talk through each of these points here very quickly. Our solution is a digital twin, but it's a system and process twin that's rendered in mathematics. The mathematics basically mimic, the components relationship together of the chiller plant, and also the input data, which is basically a wet bulb and dry bulb, and your heat load data, and also outcome. Outcome, of course, will be the temperature that you expect in the space, right? Number two, I already shared, that we cover the chiller issue and the space air area. We use machine learning. This fourth point here is closed loop, fully automated. What it means, is after we install the solution, from gathering data in a real-time basis to running, for the lack of better words, simulation, to reaching a new set point, writing back to the BMS, every 5 minutes that happens, zero human intervention. Right. In fact, on top of that, the reason why we call it closed loop is not only just because from gathering of data, running a simulation, and also writing back BMS, our use behavior, the heat load changes all the time. Our weather also change all the time, right? So the system actually recognizes, past period. There's a recent past period, whether the use behavior has changed, weather behavior has changed. If it has changed dramatically away from the model itself, the model will retune and reflect the current use behavior and also the current weather pattern. That's why we are able to maintain the accuracy level of the model, right? So closed loop meaning is full automation there. And as far as baselines is concerned, we do not use last year's same period, because that may be inaccurate, right? What we do is a dynamic baseline. The reason why we can achieve that is because, we take in data, let's say for your last 6 months or last 1 year of your equipment behavior according to all heat load and all weather condition. Right, so it basically produces a polynomial a map or graph of the behavior of that particular asset, that particular set of equipment. Right? And because of that, we know what the baseline will be under every single condition. So we use a mathematical approach which is quantifiable. So when we say we saved 5%, we can prove it is actually 5%, and how do you arrive at that? So basically, machine learning and data approach is a quantitative approach, so you can actually, have a backward audit and see how do you arrive at those information, right? And I've shared earlier, our solution is highly accurate. In some instances, we even achieve less than 2.5% error margin. So what are some of the value proposition? I talked about self-learning algorithm. I talked about machine learning is much more accurate. Number two is a process and system twin. It's not a beam twin, right? And we run a closed-loop system, fully autonomous, zero human intervention. It's very efficient because it's a software. Upfront investment and installation cost is very low. In fact, we don't even charge. Right? And the way we charge for this particular solution, is that every dollar you save, we like to share a bit of the savings with you. All right? And the reason why you can achieve that is because it's highly accurate. It's a software solution, and it does. If your building is already a Green Mark certified building here in Singapore, you basically have the data which we need. All we need for requirement is that your sensors are doing what it's supposed to do, right? Fast installation and implementation, I talked about that. High confidence, no savings, no pay, and zero upfront investment. I talked about that earlier. I'll skip this. Our solution is also SGBC certified under the Product for Digital AI platform. Last year, we were winner of ASEAN Energy Efficient Building under Cutting Edge Technology Award. Right? Our achievements so far, these are a number of buildings in our solution. So not all the buildings here, for example, use a HVAC, but we have a number of different solutions. But these are the, the space, in Singapore, in Malaysia, and also in Australia, which use our solution so far. Right? I'll have my colleague, CK.
Thanks, Bill, and good morning, everyone. Right. Okay, so for the remainder of the session, right, we will share 2 case studies, right? So with a little bit of experience and also, what we have achieved in our past implementation. Okay, so the first case study, right, we deploy a chiller plant optimization solution onto a building in the CBD area. Okay, so we all know to improve the plant efficiency of a building, there's a lot of way to doing it, right? You can simply replace, a piece of more efficient equipment, or you can do a thorough maintenance or improvement regime, to bring the efficiency up. But this is not what we do, okay? So for this specific project, the objective is to apply data analytic techniques and machine learning techniques, right, to improve the plant efficiency. Okay, so we are not doing any retrofitting. Okay, so a little bit of profile of this building. This is a 19-story building, Green Mark certified, Platinum certified, and also the floor area is about 35,000 square meters. Okay, the building is built in year 2009, and it's an office building, right? So the office hour operating load is between 500 to 650 ton, and office hour, when I say office hour, it includes night and evening, right? It's between 50 to 150 ton. Okay, so the building is cooled by a water-cooled chiller system. Consists of 4 chillers, 4 set of pumps, 1 on condenser side, 4 of condenser sides and 4 on the chill water side, and also 2 towers. Okay, so the table below here, right, show the original way of the chiller plant is being operated when we take over the project. There will be 2 chillers in operation, in the peak hour. So peak hours covers 5.5 days, Monday to Friday, 7 a.m. to 6 p.m. And then over the Saturday, half day, 7 a.m. to 1 p.m. Then the remaining of the day, there will be only 1 chiller in operation. Okay. Okay, so the first step, right, like what Bill have mentioned, right, before we start working on something is of course we need to run the assessment, right? So the table on the left is a quick summary of the building operating profile. So the building uses total of 2.5 million tons every year, and then consume 1.8 kilowatt hour per year solely on chiller plant, right? So the total utility cost, if you were based on tariff rate of 0.34 kilowatt hour per dollar, then that sum up to total 610 Singapore dollar. Okay, so instead of using the conventional baseline method, right? Okay, we use a method we call dynamic baseline. So how it works, right? Basically, instead of a fixed set point, we look into various factors, which include the load, the weather, and also the equipment condition. And the polynomial plane that Bill had mentioned earlier is, shown on the right. That helps you to visualize, right? So with all these relationships being rendered, we can accurately predict or calculate what is the consumption that the building should be using under certain condition. Okay, so these are the results. I think I'm running out of time. So column A is the consumption, and as what Bill said, we don't limit or curb the consumption, right? So we don't say the owner cannot use aircon, for us to reduce the kilowatt. So what we do is actually we optimize the way the plant is being operated. And the result, we skip right to the column, last column there. So you can see the average saving is about 12 to 13%. But one trend you might observe is that the savings is actually increased as time goes. So the beautiful part about data analytics, right, is that as the data is getting richer, the solution will get smarter as well. That's why you see the saving is increasing month after month. Okay, second case study, right? I quickly touch on this. So this is on AHU operation. So we optimize and AHU is being operated. So because of specifically to this case, right, because of the limit of available sensor on site, we use simple kilowatt method in time series to construct the baseline. Okay, and as we all know, there's various type of SI in the market, right? So depending on the type of the configuration, the strategy might be a little bit different. Some allow us full degree of freedom to do control and optimization, some lesser. Okay, let's focus on the column on the right. So this is the result that we achieved specifically for this case. Okay, so total of 6 month data, and also the savings is on the right. I have to clarify that the savings look very, very attractive, but the project has been undergo certain retrofits. So some of the issue is actually oversized. But generally, for the fan, right, the fan operate based on affinity law, right? So with this nature, every reduction in fan operating point will actually lead to substantial or attractive energy saving. Okay, so this is a simple chart to show, if you have question on how we install, how complicated the system is and how it pulls and write data, we can have more discussion later at the booth. I think with that, that is all for my presentation. Thank you.